These black and white squares are not decoration. They are camera targets. On NASA's Space Launch System, some are tiny. Others are as large as 3 feet across. Together, they let engineers turn launch footage into measurements of a rocket twisting, flexing, and separating at high speed. Look at the twin solid rocket boosters. The checkerboards form crisp corners. The left booster even has a black ring near its nose, so engineers can tell left from right when the camera sees only a tight slice of an almost perfectly symmetrical vehicle. In real launch footage, those marks can disappear in smoke, glare, and distance in seconds. Before they do, multiple cameras lock onto the same points. That is the first clue. NASA did not paint a pattern for us to notice. It painted something a computer could follow. If you like finding hidden engineering clues in real footage, subscribe. That is exactly what we decode here. The idea is older than digital video. Early rockets used bold black and white roll patterns so observers on the ground could see whether the vehicle was rotating. A plain cylinder can look almost identical after it turns. An asymmetric stripe cannot. Saturn V carried black markings across all 3 stages. As one stage separated, engineers could use the pattern on the next stage to track the rocket's orientation and roll. But paint is not free. NASA learned that dramatically with the Saturn V test vehicle. Its tall black T-shapes and a horizontal black band absorb sunlight. The dark areas cause significant overheating inside the rocket, so workers covered parts of the black scheme with white paint before later flights. That is why these patterns are never just branding. Their shape, color, and location have to deliver useful data without creating a new problem. Modern SLS markings are designed for photogrammetry, measuring 3-dimensional motion from images. The basic idea is simple. A black square against a white surface creates an edge that remains easy to detect. A soft curve or a logo gives a computer fewer exact points. A corner gives it 2 sharp lines meeting at one repeatable location. Now add another camera. If both cameras see the same corner from known positions, engineers can form a triangle and reconstruct where that point moved in space. Add more markings across the core stage, boosters, and mobile launcher, and the video becomes a moving coordinate system. NASA's Artemis reference guide says the markings range from 0.2 of an inch to 3 feet by 3 feet. The multi-checkered patterns on the solid rocket boosters are about 24 inches tall and 130 inches wide. They are sized for different cameras and different distances. Watch one square frame by frame. The image is not just showing the rocket move. Its pixels can be compared with the predicted motion from a computer model. The targets are useful before liftoff, too. During a wet dress rehearsal, NASA loaded more than 730,000 gallons of cryogenic propellant into the rocket. Cameras watch reference points while the enormous structure took on the cold fuel and the loads changed. Engineers could study how the vehicle responded without touching it with another sensor. At launch, the problem becomes harder. The rocket shakes, bright exhaust can wash out detail, and every camera sees a different angle. High contrast marks give the imagery teams common points to track through those conditions. Then, the view changes again at booster separation. Onboard cameras may see only a small section of hardware. The black ring identifies one booster. Checkered rings provide scale and orientation. Engineers can reconstruct the separation trajectory frame by frame and compare the real clearance with the model. For darker separation events, paint is not always enough. NASA also uses retroreflective targets. They return light toward an onboard camera's own light source. The same basic reason a road sign can appear bright at night. One visual language, several jobs. Identity, position, rotation, distance, and clearance. So when a real launch clip shows black squares, a checkerboard, or one odd ring, you are looking at part of the measurement system. The spectacular image is also engineering evidence. The old version helped human observers see a rocket roll. The modern version gives software sharp corners to track. Multiple views turn those corners into 3-dimensional motion. And the placement changes when heat, cold, lighting, or camera angle changes the problem. That is the hidden story in this footage. Cameras are not only recording the launch. The rocket has been designed to make the recording measurable. Next time, do not just watch the flame. Watch the marks that remain visible for the first few seconds. They may be telling engineers exactly how the rocket moved. What real science footage should we decode next?